All right, let's dive into chapter 2, which is all about the electric field. The trickiest thing with this is just the basic idea of a field, or the concept of a field. And a field is really just a region that has a unique value at every point. And really it would be a 3D thing, but often in problems, most of the time actually, we would just look at 2 dimensions at a time. One of the sort of easiest ways to get into this concept is to first talk about the idea of a gravitational field. So this whole chapter is on the electric field, but it's easier to talk about something we already know to start. So that's why I'm going to start by looking at the gravitational field. If you are standing at a certain place and you have a baseball or something in your hand and you want to throw that ball, then we basically have a projectile motion, and this is something that's fairly straightforward. We can observe this, in everyday life, and there aren't too many surprises. We have this basic idea from our everyday experience that if you throw something up, then it will eventually fall down, and we say that's due to gravity. So if I have a person standing there and they throw a ball with an initial velocity vi, then that ball will actually describe a parabolic trajectory, reaching a highest point, and then falling and hitting the ground somewhere down the line. When I was teaching mechanics, I would often include the following question on a quiz or a test, and I would basically say and ask my students to draw a free body diagram of an object in projectile motion at its highest point. And it's a trick question, because the whole point with projectile motion is that the only force that's acting is the force of gravity. And so gravity points straight down, so we would just have Fg, and we can quantify it as m times g. Many times we would actually write this out, Fg is equal to mg, or sometimes I would actually just use the formula, the variable w for weight, m times g. And people had the general concept, okay, g is 9.8 newtons per kilogram, or often they would say meters per second squared. But g was always 9.8 or 9.81. If you're simplifying the math, sometimes they'd substitute in 10. And I would always get a bit more picky, and I'd say, well, actually, it should be 9.8 and then newtons per kilogram because we're multiplying kilograms and we're getting newtons. And I would say because it's a vector, we have to include the direction. And the direction for projectile motion is down. And that's the extent of the trickiness. What the students didn't realize is that this vector g, 9.8 newtons per kilogram down, is actually describing the gravitational field. Every point along that trajectory has g going down. And this is valid for projectiles when you're not moving very far away from the Earth's surface. Maybe you have heard of the concept, if you go to the top of Mount Everest, for instance, then the value of gravity will be a bit different. If you have a really super tall person, or just find a way to climb up to, say, 300 kilometers, and you're able to throw a ball in the same manner as what we just did, you could actually throw a ball with some initial velocity. And if you throw it far enough, you could actually reach partway around the world. So in that case, gravity isn't just sort of down towards the bottom of the screen. In that case, if you throw it a little further, in fact, it can reach further around the world. If you throw it, I should say, faster each time. If you throw it much faster, it can cycle most of the way around the world. And if you throw it really, really fast, it can get to a point where it doesn't actually ever hit the world. I think this is Douglas Adams. Wow, my circle is really awful. Anyway, this is Douglas Adams' version of flying, which is falling but continually missing the ground. And this is actually how low Earth orbit works. You get something like a space station, get it moving fast enough, 300 kilometers above the Earth's surface, and if it's moving fast enough around the Earth, then it will not hit the Earth. In this case on the right, clearly g, the gravitational field, isn't always down towards the bottom of the screen. And really the way it works is that g is towards the center of the Earth, or the Earth's center of mass. And so as the ball or the space station or whatever it happens to be goes around, the velocity is continually affected by this force of gravity. And it's continually bending the velocity towards the Earth and it goes around. So this portion on the right describes the gravitational field close to the planet Earth. The neat thing, or the important thing to notice about this, is that G, the gravitational field, is independent of the projectile. So again, remember we have F of G, the force of gravity, is equal to the mass of the projectile times G. And the force that that object feels depends on the object. So if you have a baseball, that's one thing. If you have a physics textbook that you want to, say, throw to the other side of the world, that's another thing, probably heavier than the baseball. If you have a chicken, whatever you have, whatever you're throwing, will have a different mass and a correspondingly different force. But notice that G doesn't change. The gravitational field depends on the Earth. The gravitational field does not depend on the projectile. If you think back to the last bit on Coulomb's law, we can recall the expression for Coulomb's law was F of E, the electric force, is equal to K times Q1, Q2 over R12 squared, and that's for a point charge. We can compare that with Newton's law of universal gravitation, which says that the gravitational force, or the force of gravity, is equal to G times M1 times M2 over R12 squared. In this case, G is a universal constant, 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. If we apply the universal law of gravitation at the Earth's surface, then we can substitute in the mass of the Earth, the radius of the Earth, and we can isolate Fg equals mg, just like what we had before, where g is 9.81 newtons per kilogram. So there's nothing really new here. This is just from mechanics, and what I'm trying to do is to show the relationship between the electric force and k q1 q2 over r12 squared and the gravitational force g m1 m2 over r12 squared. Because the next step then is that we can write Fg is equal to mg, and we can also isolate g in terms of the gravitational force acting on mass m divided by m. And g is the gravitational field, which is 9.81 newtons per kilogram down at the Earth's surface. And the down is important because it's a vector. Similarly, for the electric force, we can express it as Fe is equal to Qe, and then isolate E to get as Fe over Q, or divided by Q, which is the electric force acting on charge Q divided by Q. In this form, Q is often called a test charge because it is used to test or detect the value of E at any point in space. We could take a charge and put it somewhere where we think there's an electric field, and if the charge moves, then we could actually measure the acceleration, and knowing the mass of the charge and the acceleration, we could find the force that was causing that, and then we could divide by the amount of charge that it had to figure out what the electric field is. And it's worth thinking about what the test charge means for a minute. And if you don't understand this immediately, don't worry. It's something that might be worth revisiting a day or two later and repeatedly. It is really important, and I see a lot of students mix up what the test charge means. If we go back to when we were throwing the ball around the Earth, in that case, the ball would be like the test mass, and the Earth would be the source of the gravitational field. And the discussion or the confusion that students often have is between which electric charges are causing an electric field and then which electric charges are actually the test charges. And if you think back to throwing a ball like Superman did in one of this, maybe the first movie, all the way around the world, then the Earth is actually what's causing the gravitational field, and the ball is the test mass that actually moves and gives us evidence that there is a gravitational field. One of the key things with the gravitational field was that the gravitational field was independent of the test mass. So it doesn't matter whether you're dropping or throwing a ball or a chicken or a 747, all of those, now with the 747 you're really tempted to not ignore air friction, but in projectile motion we're ignoring air friction. All of these objects feel gravity. They feel different forces because of the different masses, but they're in the same gravitational field. So G is independent of the test mass. Similarly, and this is another key thing that many students have trouble with, the electric field is independent of the test charge. So if I set up an electric field with a certain value in terms of newtons per coulomb, I can take lots of different charges. I could have a -9 microcoulomb charge. I could have a positive 15 nanocoulomb charge. I could have a positive 1 coulomb charge. all of these feel the same electric field. For gravity, remember, we had the force of gravity was equal to the mass, we can call that the test mass, times the gravitational field. For the electric force, again, we have the electric force is equal to the charge, so that would be the -9, the 15, or the 1, times the electric field. And now these ideas have confused many, many students in the past, and I'm sure they will confuse many students in the future. So the concept of the electric field confuses many students, so don't worry if it's weird at first, but do try to review it often at the beginning of your semester. It'll definitely pay off.